Recording is rolling. Welcome to Friday. A lot of you guys already turned in your chapter 6-7 homework. If you haven't done that yet, you can pop that in the grade tray in a couple of minutes. Okay, you guys remember your take-home quiz is due on Monday. And most of today, I'll set you guys up with the turntable out, but one more time for you guys. Well, I'm still talking to you guys. Remember, one of your quiz questions, one of your take-home quiz questions, one of the first 5 questions involves, well, it references the centripetal force lab that you guys did, navigating this equation. Now, I did go over this with you guys yesterday. Let's look at just a few more examples, just to get a few more examples in. All right, so this was the answer to your guys' last lab, centripetal forces mv squared over r. And I asked different versions of this question, so I don't know exactly which one you got, but it has something to do with what's the relationship between 2 variables. So suppose, we'll look at 3 examples. Okay. Suppose force increased by a factor of 9. We're going to leave V and R the same. How would the mass respond to maintain balance? Okay. Now, this is a proportional question that should work in general for any answer. So I showed you guys a trick yesterday, which is that, well, if it works in general for any answer, then it should work for any particular numbers, any particular solution. For example, 1 Newton might hold in place a 1 kilogram mass swinging at 1 meter per second in a circle with radius 1 meter, right? So, I mean, obviously that should make sense, right? So if you up force by a factor of 9 and leave V and R the same, then it should stand out right away. Okay, well, mass must increase by a factor of 9. Now that's a pretty straightforward example because force and mass are directly proportional. But what about some of the other relationships? So let's do a couple other examples. What if I said what's the relationship between F and V? So same idea, increase force by a factor of 9, so that hanging weight in your centripetal force lab. But this time let's leave M and R the same. How would V respond? So same example, starting point, it increased force by a factor of 9, but this time leave these 2 variables the same. You guys see that the speed would have to triple in this case, go by a factor of 3, because 3 being squared would restore balance. Is that? Okay. And then one more of these examples. Let's say you want to look at the inverse relationship. So same idea, increase force by a factor of 9, but this time we're going to leave everything in the numerator the same. Do you guys say that the radial size would have to be, well, 1 over 9? Okay, so 1 divided by 1 over 9 would be 9, so that would restore balance too. Okay? So yeah, that's one trick you can use to figure out that question pretty fast. Okay. All right, turntable lab. Do you guys have on the side of your desk a page that looks like this? Okay. So this is what you guys are doing rest of today. So get you guys set up and show you exactly what's going on, how to do this. Okay. So I've got this turntable. This thing can spin. So do it counterclockwise. It's sort of the positive direction from your math class. Okay. And I could throw different stuff on here. Okay. I got coin. I got a binder clip. I got this eraser. Little knicks-knacks around. Okay, guitar pick. Right. So if I give this a spin, which one of these objects do you think would be the last to fly off if I spin this faster? Probably I'm thinking this eraser because it's just it's probably gonna stick. I don't actually know. I haven't actually tried this out, but yeah, let's do this real time. Let's see which one flies off last. Oh, well, that was way too fast. All right, totally overshot it. Let me try one more shot at that, and then try it again. All right, so give them all about the same, approximately same radial distance from the center. All right, but not exactly, pretty close. All right, let's see. Okay. Ooh, so the coin binder clip first. Now it's a standoff between this pick and this eraser. There goes the pick. Yeah. Okay. So that is true. So probably between the eraser and this wood surface has the largest coefficient of friction. Huh. I wonder how you could quantify what those coefficients of frictions are. Well, if you can follow the logic of this table, then this very last column will tell you what the answer is. So, hey, look, it's exactly the setup you guys just saw. Got a turntable spinning at some omega rate. There's some object here. This free-body diagram. Okay. How are you going to get coefficient of friction? Well, you can do different trials, and I'm just going to have you guys do at least 3. You should have plenty of time to do this, and then if you have any questions about anything in the class, you take on quiz, whatnot, then that's what take. And then instead of trial number, put some object. Like, for example, I had a coin. There was a binder clip. The eraser was when I was interested, just like different objects. Okay. Then, now you guys know gravity field 980 centimeters per second squared. I'm gonna have you guys measure in centimeters today, just a little bit more intuitive. Measure the radial distance of that object from the center. Is that? So in this case, my center is like right about here-ish. This eraser is about, looks like, oh, center mass is 10 centimeters from the center. So I'd put 10 for 10 centimeters. Okay, we'll just do centimeters today. Right, that'll be consistent with that gravity field unit of 980 centimeters per second squared. Okay, and then spin that turntable until it's just fast enough where that object breaks friction and slides off because of its own inertia, right? Its first law of motion. Right? And at that point, figure out, well, you want to figure out the spin rate for that. And the way you're going to do that is to say, you're going to time it. You guys brought your stopwatches today, right? Like, just for this lab. So I wonder how much time it would take to make one revolution. You guys could probably time that. Okay. If you can figure that out, then write that time, do a few trials and take an average. Okay. And then if you know that time to make one revolution, well, remember that the equations we're using are in like radians and radians per second for the rotational values. So that's why this column is just defaults to 2 pi, because the 2 pi radians is one revolution. But you guys know that, we talked about that, right? So then, if you know it spins 2 pi radians, which is one revolution, and you know how much time it takes to do that at the point that object breaks friction, okay, then all you have to do is divide these two columns to get omega, the spin rate in radians per second. It says above this column exactly what to do. So it's just do theta divided by t. Okay. 2 pi radians divided by how much time. Is that okay? That makes sense? Okay. So at this point, you'll know everything you need to know. You'll know the distance from the center. You'll have calculated the angular velocity by doing 2 pi radians divided by how much time to spin around once. Okay. Now to get coefficient of friction. Turns out that's all you need. Notice I did not give you a column for mass. Maybe I should have, but mass ends up canceling out and not making a difference in the end. I did give you guys this proof right here. Let me zoom in so you guys can see that. Okay. So this is the logic that will lead to this very last expression that will allow you to solve for the coefficient of friction. So this frictional force is acting as the centripetal force, of course, until it breaks friction and slides off, but right up to that breaking point. Okay. Now, friction force, you guys know, is coefficient of friction times the normal force. That's what will eventually allow you to solve for mu. Okay. And centripetal force, well, you guys have this expression, m times omega squared times r. Then, well, normal force, you guys know, is just equivalent to the weight, so you can sub that in. Then, here's where the mass cancels out. That's why I was not having you guys record the mass, although that would have been good scientific practice. But then divide both sides by g, and there you go. That is how that is the derivation for how you're going to get coefficient of friction. And all these values you have because omega, angular velocity, you would have calculated. That's the previous column. R, the radial distance from the center, you would have directly measured. And g, I'm telling you guys, is 980 centimeters per second squared. You pop it in, pop, pop, pop. What would be a reasonable number, do you think? I mean, obviously different objects are going to have different coefficients of friction. Coefficient of static friction, I should really say. But you saw that. Like you saw the eraser probably has the greatest, well, between the eraser and the wood surface, it's probably the most out of those objects that I showed you. What's a reasonable number to look for in this column? Maybe like 0.3, 0.4, 0.5, maybe somewhere there. Okay. If you get numbers in about that ballpark, then that is really good news. All right, you guys got any questions about? Yeah. No?
Does G equals 10?
Okay, yeah, that is a great question. So gravity field, we've been usually using 10 meters per second squared, but you guys know that's really a rounded version of 9.8 meters per second squared. And today, since I'm having you guys measure radial distance in centimeters, because that's probably the most intuitive way to do it, just like, it's like 10 centimeters or 9 centimeters or 12 centimeters. Then I gave you guys gravity field as 980 centimeters per second squared. So that's what you're using for gravity. The number is 980 and the unit is centimeters per second squared. Okay. All right, guys set? Okay. So you guys wrote in your planner, quiz due Monday. Some of you guys already turned in the quiz, so if you have, that's awesome. But if not, then due Monday. Any questions? All right, so you guys got the rest of the class to do, again, just pick at least 3 objects, turn this page into the grade tray by the end, and that will carry us all the way to the weekend.